Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's a pleasure to have Nigan Salachiket visiting us. Megan is from UMass, and she works with Kevin Fu, who's also visiting us, and she'll be speaking about security for RFID.
Thank you. Hello, I'm presenting CCCP, Secure Remote Storage for Computational RFID tags. This is a joint work with Shane Clark, Ben Ransford, and Kevin Fu from University of Massachusetts Amherst, and Ari Jules from RSA. So before I begin, let me give you a high-level view of the work. It's sometimes more efficient to do something remotely instead of locally. For example, it's cheaper in terms of money to ask China to build some products for you and ship it to the United States instead of producing that items in the United States. So here efficiency means money. Another example, a more technical example, it's faster to store something in remote RAM via networking instead of storing that in the hard drive. So here by efficiency, I mean time. So those are two well-studied examples. I'm going to introduce a new example here, which is in RFID tags. It's more energy efficient to store something remotely instead of storing that locally into flash memory. I'm going to focus on that example and tell you that if you want to store something remotely, you need to have some security. You need to consider security. So let's see what kind of devices I'm talking about. I'm talking about batteryless RFID tags, and they are for identification, and these devices usually are scanned by RFID readers, and they send back an static ID so that the RFID tags knows what's scanning and what items it's talking to. So how could we make these RFID tags more powerful? They don't have a one Neumann architecture. So maybe if we add a microprocessor to them and then add some flash memory and non-volatile storage to them, and maybe some sensors like sensor temperature, humidity, so that they can monitor the environment, we will have a more powerful batteryless RFID tag. Well, Intel has done that. They have built Intel WISP, which is wireless identification and sensing platform, which in general we call them computational RFID tags. So let's see some characteristics of these RFIDs. They are essentially batteryless mini computers, and since they are batteryless, they are maintenance-free, meaning that we can simply implant them inside the bridge without worrying about changing the batteries from time to time. So, and since they are batteryless, they need to harvest their energy from somewhere, from the RFID reader that they are interacting with, and store that harvested energy in a small capacitor, which is leaking. So, as we know, capacitors leak energy in exponential decay. So in few seconds, the CRFID tag loses its energy, whether it's used it or not. So let's use that energy to do something good. So these batteryless mini computers are small, they are maintenance-free, they are nice, we can use them wherever it's difficult to access, but there is an issue here. The local storage, the non-volatile storage that CRFID tags are using is energy intensive, meaning that the write operation is much more expensive than the read operation. So if you are going to store something, you need to spend a lot of energy. And if I tell you that the read operation is almost the same, consumes the same amount of energy as the CPU operation, you can see that flash memory is much more expensive than a CPU. There is another issue. This non-volatile storage, it's write once memory. meaning that if you want to reuse that memory, you need to first erase the memory and then write something. And as you can see, erase is also an expensive operation. So storing something basically means erasing the memory and then writing something, and they are like the two most expensive operations available on the CRFID. And finally, this energy expensive local storage is very small. Currently, we have about 32 kilobytes of flash memory available on the VIS platform, which about 1 kilobyte of that is assigned for information memory. So we are looking for an alternative to this storage, something low cost. In the rest of the talk, I'm going to tell you how we can provide CRFID tags with a secure remote storage, and then how could we use this secure remote storage to make CRFID tags more powerful. So if we look at the cousins of CRFID tags, sensor modes, we can see that there, the main component that's the most power-consuming component is radio. So there it makes sense to avoid radio as much as possible and instead try to focus on CPU and flash memory. But if we look at CRFID tags, surprisingly, radio is very cheap. So why not use radio and focus on radio and avoid flash? Yes, go ahead.
Can you define the mode? I heard half of it in 1 ear.
Yes, so a mode has batteries. It's like a mini computer, but it has batteries, which they last about several months, and they are also very restricted in terms of their resources. They have very limited amount of RAM and tiny flash and low bandwidth, and as we can see, their radio is very expensive. So
essentially a mode is an RFID with a battery.
Yeah, I guess so. Maybe an RFID is a mode without a battery. Okay, so in a CRFID tag, radio consumes less energy than the local storage. Let's outsource our storage to a reader. Since the memory is cheap and abundant in RFID reader, we can save a lot of energy on the CRFID tag by just focusing on the radio and outsourcing the storage to a radio. So it should be simple. The CRFID tag sends its data via radio to the RFID reader. The RFID reader stores that data for the CRFID, and then later on, the RFID reader sends that data back to the CRFID. But what if the reader doesn't send back the original data to the CRFID? So there's a problem here. A reader is not necessarily trustworthy. We need to provide some security and make sure of some essential security goals here: integrity, authentication, confidentiality, data freshness. And by data freshness, I mean that the tag needs to make sure that it's receiving the latest data that it has sent to the reader, so that CRFID, the RFID reader or any other third party is not going to do a replay attack on the CRFID. And availability, but we are not addressing availability in this work. It's more like denial of service attacks. It should be simple to provide those security, to provide the CRFID tag with these security goals. But remember what devices we are talking about. They don't have any battery. They have a tiny capacitor to store the harvested energy. They reboot every few seconds. They have a small RAM, expensive flash memory. Their communication is non-autonomous, and it's low bandwidth. So considering all those resource limitations, how could we provide security to the CRFID tag? We have a hypothesis, and that is it's possible to provide the CRFID tag with a remote storage that is secure, and still it's less energy consuming than storing something locally. So we hope that we can use the already developed security modules so that we provide the secure remote storage, and the security overhead does not overshadow our savings from using remote storage instead of local storage. So the first goal is confidentiality. We chose to use stream ciphers here. And particularly, I'm talking about XOR, simply XOR your data with a pseudo-random key stream. XOR is a very energy-efficient operation, and the only challenge here is that we need to somehow provide CRFID tags with key streams, with pseudo-random key streams. So there are like random bits that you are going to XOR your data with that and protect the confidentiality of your data. But computing the key streams is energy intensive. So we need to somehow avoid computing the key streams on runtime and somehow provide CRFID tags with key streams. I'm going to address that later. The other security goals, integrity and authentication. So the typical solution would be use HMAC, SHA-1, or other MAC schemes, but they are memory and energy intensive, especially if the data that you are working on is small. It's going to use a lot of memory in the beginning. So we chose to use universal hash function-based MACs. And the way it works, you call the UHF on the data, and you XOR the hash result and the key stream, and you make your message authentication code and send that to the reader. So particularly, we use UMAC, which is fast and energy efficient. We have implemented that on VISP, and it works well. So again here, there's a challenge, and that's, again, we need to provide the CRFID tags with key stream. But if we can do that, if we can provide CRFID tags with key streams, we are solving two problems. Next, we need to provide the tags with data freshness. So in that case, we need to keep some sort of a state to make sure the freshness of the data. But we need to store that state locally, because the CRFID tags only trust itself and nobody else. But if we are storing something in non-volatile memory locally, that means using the flash memory again, and then we are back to square one. So how are we going to address that problem? First of all, we are trying to keep that state for the data freshness as minimum as possible. And next, we are introducing a new approach called hole punching. So basically, if you are storing something in binary mode in the memory, let's say you have a stored number 7 in a binary format in your memory, and then you want to store an 8, that's not possible, because you need an erase before you can write anything to the memory. Well, you can see here, you need to change the force bit, that is 0, to a 1. And you cannot do that with a simple write. You need to do an erase first. But if you store, so you do an erase and then store your number 8 there. But if you are storing your number in unary format, which is like punching 7 holes into your memory and then represent number 7, and later when you want to store 8, you just need to punch another hole to have 8 holes, which represent 8 in unary format. So using hole punching, yes?
If erase only costs as much as write, and implied by a previous slide, if you're going to erase individual bits, then gray code would get you within a factor of 2 of binary counter.
But erase works in blocks. So it erases one block, which sometimes is about 128 bytes. So using hole punching, we are avoiding erase, and we are changing 1 bit at a time, which is more energy efficient. OK, let's go back to that key streams that we said both the MAC scheme and the encryption scheme needs those pseudo-random key streams. And we know that as long as we don't reuse the key streams, we are safe. Apparently, United States was able to decode the messages from Russia since they were reusing the key streams. So we don't want to make the same mistake. Let's say there are some good power seasons that tag has enough energy and it's able to compute its key streams by calling a block cipher, store that key streams in flash memory, although that's energy expensive, but we are in a good power season, and then erase the old and used key streams. So whenever the tag has enough energy and it's in a good power season, and I'm going to define that, it's going to opportunistically pre-compute the key streams. And later on, runtime, the key stream, the MAC scheme and the encryption scheme are going to use the key streams and protect the security of the CRFID. So what do I mean by good power season? There are times when the CRFID tag is idle. So for example, CRFID is awake, it has harvested some energy, but it doesn't have anything to do anymore. So it can just use that energy and pre-compute some key streams and store them into the flash memory. Or another example, maybe CRFID is close to an RFID reader, and it's harvesting energy from that RFID reader, but the RFID reader doesn't speak the language of that CRFID. It doesn't know what encryption scheme, what MAC scheme the CRFID is using, and it doesn't have access to the data that CRFID has stored. So still the CRFID tag could harvest energy from that RFID reader, but it cannot talk to it. It cannot send anything data. So it can just use that energy and opportunistically pre-compute some more key streams and store them into the flash memory. So far I have addressed the security goals. I've told you how to make a secure remote storage for CRFIDs. Now I'm going to tell you how to use that secure remote storage to enable CRFIDs to do general computation and become more powerful. CRFID tags can do some cryptography. For example, we have seen that we can implement and run RC5 on WISP. But could they do any larger computation? Could they run public key cryptography with that small amount of energy that they have available? Could they do modular exponentiation? Well, the answer is no, and that's because they have a very small leaking energy storage, and since this storage is leaking every few seconds, the CRFID tag loses its power and loses whatever it has computed so far. So it forgets what it has computed so far. So the goal here is computational progress. We want to make sure that the CRFID is able to finally finish a program, meaning that, and by computational progress I mean change of computational states towards a goal. For example, completing a loop for a CRFID. So in other words, I mean, we want to eliminate the Sisyphean task, which is rolling our computation and then a restart happens, and we should redo all the computation that we have done so far. Well, there is a work called Memento-S, which introduced a solution here. If you have seen the movie Memento, there is this guy who suffers from short-term memory loss, and he just needs to take notes and tattoos information on his body so that next time he wakes up, he can read those tattoos, remembers what he was doing. So the idea here is similar. The CRFID tag has some tasks to do, has some energy. It starts doing some task, and then it finds out it's losing its energy and it's going to die soon. So it takes some notes, it checkpoints whatever it had computed so far into local flash memory, and then it dies, it loses its energy. Later on, it receives more energy, it harvests more energy, it retrieves the information from flash memory, and then it could continue its task. So something like public key cryptography can be possible using this approach by finishing your computation over multiple life cycles. But the problem here is that Memento-S uses flash memory, and flash memory is energy intensive. So could we do any better? We can use the secure remote storage, and that's what CCCP cryptographic computational continuation passing is about. Use the secure remote storage and checkpoint your information remotely to be able to do more computation. So the CRFID sends computational state to a reader, and then, but that's not going to happen because the CRFID cannot start a communication. It does not have autonomous communication. It must wait for the RFID reader to start the communication. So the reader sends a query, and along with that some energy to the CRFID. CRFID harvests energy, use that energy to do some task, and then says to the reader, I'm losing my energy, I need to store something. The reader says, this is the message size you can use, and the CRFID encrypts its data, constructs a MAC, and sends the ciphertext and MAC to the reader, and the reader stores that information for the CRFID. Later on, when the CRFID wants to retrieve its information, the reader sends, when it sees the CRFID tag, sends ciphertext and MAC to the CRFID along with some energy. The CRFID verifies the authentication and authenticity and integrity of the message, decrypts the data, finds its computational state, and continues its task, and finally finishes whatever it was computing. So far I've told you how to make the secure remote storage and how to use that to make CRFIDs more powerful. We've done some experiment to see if that secure remote storage consumes less energy than flash memory. So the experimental setup was like this. We programmed the VIS with a task which was storing locally or remotely, and then we give it, we charge the VIS to 4.5 volt, and then we let the VIS run alone without access to any voltage, any energy supply, and then we observe the voltage drop and execution time of the VIS, and half of CV squared, we use the information, we computed the energy consumption of the VIS doing that task. So here are the results. The red line is the secure remote storage in a full mode, protecting confidentiality, authentication, integrity, and data freshness, and the blue line is local storage. So as you can see, somewhere between 64 and 128 bytes, there's a cross bond, and after that, the secure remote storage stays below the blue line, which shows that it consumes less energy than the local storage. And the blue line here, it just represents writing to the flash memory. It assumes that the memory is fresh and you don't need to do any erase. So it's the best case for the flash memory. We also implemented CCCP with just authentication. If you just care about the authentication and integrity of the messages you are sending, and that's the purple line. And the no security, just reusing the secure remote storage, and that's like the baseline for CCCP and any other protocol that use remote storage. Everything would stay above the green line. And finally, if you are using flash memory, you are doing erase and write. So that the black line is the worst case scenario for storing locally. So everything that's using local storage would stay between the blue line and the dashed black line. So showing you the results, I'm going to conclude my talk. We've seen that local storage is energy expensive for CRFIDs, and surprisingly, the radio is cheap, so remote storage is a low-cost alternative for the CRFIDs, and we were able to provide CRFIDs with a remote storage, which is secure, and yet it consumes less energy than the local storage. So with that, I take questions. Yes?
The power ratios you quoted are the technology of the chip in the WISP.
Yes.
Now, every year, Moore's law shrinks the transistors in the computer, does not shrink the transistor used for the radio frequency, because it has to work with a real antenna. So how many years of Moore's law before your advantages go? The black line clearly, between the black and the green, I see you have a few years to do business.
Well, the radio is using only the radio technology that CRFID is using is just one transistor.
But a big one.
I don't know about that.
I'm pretty sure it's a big one.
It happens to be a big one, but it's changing the impedance of the antenna.
Yeah. Yeah. So it has to, if it turns, okay. It's not going to shrink by Moore's law, I guarantee you that.
Yeah, I'm not sure. Probably not.
Sorry, I'm playing devil's advocate as usual.
So any other questions? Yes.
Not really a question, but recently an Air France jet went into the Pacific, and they have everything in local flash ROM, which is sitting at the bottom of the Pacific, and they claim it's too difficult to broadcast on the radio, and I know they're lying, but If they broadcast it, they would have had the black box available in Paris headquarters.
I'm not sure if you'd be using CCCP though, because
No.
harvesting energy from 2
No,
miles under the ocean might be
No,
difficult.
no. You do
with
it
the battery?
while the plane is running.
Oh.
What is the claim width to expense to broadcast?
I'm sorry?
Just like the distance is too far? What is the claim width to
You know,
expense
the
to
real claim
broadcast?
is that pilots don't like management snooping, and management don't like lawyers snooping. So they say you can't afford the energy to transmit.
Well, my guess is
Well-
they also don't know how to get their security right, so
Maybe.
broadcasting those details might not be so good.
Okay.
Secure.
It would be a fun DTN to build plane to plane.
No, it's plane to
For
something.
instance, yes.
You don't have line of sight without a plane.
Hmm.
Okay. More questions?
Thank you.